we have seen two algorithms concerning single source shortest paths, where we fix the starting point and we look at all the paths which are from that point to every other vertex. We said the other class of shortest path problems are all pairs, right. So, in the single source shortest path, you can imagine that you have a warehouse or a factory from which you are shipping things, and you want to find the shortest way to reach every destination from that fixed place. Whereas if you are running this travel service kind of thing, you need to be able to answer questions about every pair of distance. You have no preference for a given source and a given destination. So, your customer will say, I want to go from point A to point B, what is the best route, and you have to be able to solve this for any A and any B. So, what we are going to look at now is this all pairs shortest path problem. So, Dijkstra's algorithm works for the single source problem for non-negative edge weights, and the Bellman-Ford algorithm, which is more expensive, works with negative edge weights, but of course remember that you cannot have negative cycles. With negative cycles, shortest paths are not defined because you can go around the cycle and make paths arbitrarily small. So, one way to solve the shortest path problem, of course, is to fix each vertex as a potential source, right. I know if I fix a source, I know how to solve the single source shortest path problem. So, there are n sources, n possible sources. So, I start from 0 and I solve it by using Dijkstra or Bellman-Ford. Then I started from 1 and I use Dijkstra or Bellman-Ford, and I keep doing this, and of course, that will give me a solution, right. But what we are trying to find is a more direct way of addressing this all pair shortest path problem, which does not require me to repeatedly rerun Dijkstra or Bellman-Ford from every starting point. So, remember the transitive closure of a relation. So, the transitive closure of a relation consists of repeatedly applying this relation, right. So, in the case of a graph, the edge, remember, captures a relation, right. That was our motivation for studying graphs, that graphs are visual representations of relationships between vertices. Whenever vertex 1 is related to vertex 2, there is an edge from V1 to V2. So, now if we represent this in an adjacency matrix, as we said before, then if we multiply the matrices, right, then we get all pairs which are connected by an intermediate value in between. So, if I have A comma B is in my relation and B comma C is in my relation, then AB and BC would have been 1 in the original matrix, and AC will now become 1 in the square of the original adjacency matrix. So, in this way, if I have the kth power of my adjacency matrix, it will tell me all pairs which are related by a sequence of k intermediate relationships, and since there are only n overall, I can look for everything connected directly or connected by a pair or connected by 3 and so on. So, if I add up these things, then I will get any pair of vertices which are connected by a path of any length, and this is what we call the transitive closure, right, A plus. So, an alternative way to do this is to actually look at how these paths evolve, right. So, we look at paths through a limited set of vertices. So, we say that B superscript k, right. So, the superscript indicates that I am going from I to j. So, here I was talking about the length of the path, right. So, I was saying that if I look at A to the power k, it is saying that there are k intermediate steps, right. So, I go from A to A1 to A2, A2 to A3 and so on. I do this k times and I will get, so if I do it one time I have A, if I do it 2 times I have A squared, if I do it k times I have A to the power k. So, the superscript, the power of k in this transitive closure computation captures the length of the path. Here I am going to capture not the length of the path, but the names of the vertices which I can see on the way, right. So, here if I look at B k of Aj, okay, what it is describing is that I can go from I to j by using vertices only from 0 to k minus 1, right. It is not telling me how many of these vertices I use or what is the length of the path, it is just constraining the choice of vertices, right. And of course, I and j are not constrained by this. So, this tells me from any I to any j, if I am only allowed to pass through 0 to k minus 1. So, I and j need not themselves be between 0 and k minus 1, they could be arbitrary, but I am only allowed to visit these vertices in between. So, it is a constraint on where I am allowed to stop on my way from I to j. So, if I say that k is 0, right, then this set 0 to k minus 1, because k minus 1 becomes now minus 1, right, that becomes an empty set, or in Python notation an empty list. If I take in Python a list of the form 0 to -1, right, this is going to be an empty list. So this basically says that I can go in B0, if I go from I to j, it means I am not allowed to use any intermediate vertices. That means the only way I can go from I to j is that I can directly follow an edge, so there must be a direct edge. So B0, in other words, is the same as this matrix A, right. So B0 is just the adjacency matrix which captures all the direct edges. Now I can calculate Bk plus 1 from Bk as follows. Right. In Bk, I already know that I can use the vertices 0 to k minus 1. Now in Bk plus 1, I am additionally allowed to use the vertex k, right. So remember that if I use k, then I am allowed to use 0 to k minus 1. So k itself is not allowed. So I am allowed to use the vertices from 0 to 1 minus the exponent. So if I am doing Bk plus 1, I am allowed to use 0 to k. But in Bk, I could already use 0 to k minus 1. So there is a possibility is that when I am allowed to use one more vertex, I do not need it, right. So I can already reach from I to j without using this new vertex k. That means that Bik is, or Bij to the power k is already 1, or I need this vertex, right. So if I need this vertex, I start from I and I can't get to j without using k. But if I go from I to k, then remember that these are all going to be shortest paths, right. If I am going from I to k, I should not need to visit anything in between, right. And if I go from k to j, I should not need to visit k again in between. And because overall I am constrained to go between 0 and k, and I have already seen the k, then it must be that I go from I to k using only 0 to k minus 1, and I go from k to j using only 0 to k minus 1, right. So either I use the fact that Bkij is already 1, or I can go from I to k using 0 to k minus 1 and k to j using 0 to k minus 1. So this gives me this way of updating, right. So Bkij is 1, right. If either Bk plus 1 ij is 1, if either Bkij is 1 or Bkik is 1 and Bkkj is 1, right. So this gives me a way of updating these things. Now what is the connection to transitive closure? Well, clearly Bn now tells me that Bn of ij is 1 if there is some path from I to j that passes through only the vertices 0 to n minus 1. But only the vertices 0 to n minus 1 is all the vertices. So it tells me that if I am computing this correctly, then Bn I comma j will tell me that there is some path from I to j. And this is precisely what transitive closure also says, that there is some sequence of intermediate vertices in this relation which takes me from I to j. So Bn is actually the same as A plus. Right? So this way of calculating by restricting not the length of the path but the vertices you are allowed to pass through in the path gives me an alternative way of computing transitive closure, and this transitive closure algorithm is called Warshall's algorithm. Right? So notice that it is not the same as the previous algorithm. They are both computing eventually the same thing, but one is doing this matrix multiplication, right. It is actually concatenating paths. It is saying there is a path from A to B and then there is a path from B to C, so there will be a path from A to C. Whereas here you are actually doing something more clever. You are saying that I am passing through a new vertex which I have not seen before, and I am combining those two paths to form a longer path. So the two paths I am combining might already be long paths. They are not just adding one. So the transitive closure is adding one edge at a time to an existing path, right. Whereas this this thing could be combining two longer paths just passing through a new vertex. So what we are going to do is use this transitive closure algorithm to compute all pair shortest paths, and this is called the Floyd-Warshall algorithm. So the Warshall algorithm is the transitive closure part, and Floyd's contribution is to show how to adapt this algorithm to compute all pair shortest paths. So together it is called the Floyd-Warshall algorithm in most books. So as we did for this Warshall's algorithm, let us compute this quantity. So there we called it B for the transitive closure part of it, but here let us call it SP for shortest path. So shortest path SP to the power k of I comma j is going to be the shortest path from I to j provided I stick to vertices between 0 and k minus 1. So earlier it said, does there exist a path from 0 I to j which sits between 0 to k minus 1? Here I am computing a quantity. I am saying this is the length of the shortest path which sticks within 0 and k minus 1 between I and j. So, as before, if the index is 0, then I am not allowed to pass through any intermediate vertex because the set 0 to 0 minus 1 is empty. So, SP0 of ij is just the weight, right. There is a direct edge, there is a weight, if there is no direct edge, it is infinity, right. Now, if I want to now calculate what happens when I go from SPK to SPK plus 1, we have again the same possibility. I do not need this new vertex. So, the vertex k, the index k plus 1 allows me this new vertex k. So, I do not need it, right, in which case the shortest path using all of 0 to k is actually the same as the shortest path I already had from 0 to k minus 1, right. So, the SPK plus 1 is actually the same as SPK, or I do need it. If I do need it, I need to go from I to j and then I need I to k and then I need to come from k to j, right. So, then I combine SPK of I comma k with SPK of k comma j. So, I look at both of these and I decide the minimum of these two to be the answer, right. So, SP, now if I look at the nth iteration of this, then again like in transitive closure it tells me there is some path which passes through all the, which is allowed to pass through all the vertices 0 to n minus 1. Here it says this is the shortest path which passes through any of the vertices 0 to n minus 1, right. So, this gives me the shortest path. So, this is the Floyd-Warshall algorithm, which is Warshall's algorithm adapted to the case of shortest paths. So, this is the same negative weight graph that we use for Bellman-Ford, except now we are going to try and compute all pair shortest paths, right. So, if I look at the 0th matrix, right, these are all the direct edges. So, for instance, there is an edge 1 5 with weight 2. So, at 1 5 I have weight 2. Similarly, there is an edge 6 1 with minus 4. So, 6 1 has minus 4, right. So, every direct edge is represented by its weight in this graph, and every non-existent edge is represented by infinity, saying that there is no edge at this point. So, now I want to calculate SP1. So, SP1 is all things which go from I to 0 to j plus I to j, right. So, either of these two is allowed. Now, if you look at 0 in this particular case, it has a peculiar property that there are no incoming paths to 0 because both the edges from 0 are outgoing edges. So, even if you allow a path to go through 0 and no other vertex, remember SP1 is going to allow me to go through only 0, no other vertex. If I am only allowed to pass through 0, then I cannot really do anything because 0 has no paths coming into it. So, I cannot get from anywhere to 0 and then go from 0 to somewhere else, right. So, therefore, SP1 turns out to be exactly the same as SP0. Allowing myself to go through 0 and not allowing myself to go through 0 have no impact. Both of them essentially only allow me to use direct edges. But now when I go from SP1 to SP2, now I am allowed to pass through 1, right. So, I am allowed to do things like go from 6 to 1 and then 1 to 5, right. So, these are both direct edges and I am allowed to use this, or I am allowed to go from say, so I am allowed to say for example go from 0 to 1 and 1 to 6, 0 to 1 and 1 to 5 again, right. So, these things become possible, right. So, things which pass through 1 now become possible. So, now if I look at the matrix, it says 0 to 5, which was earlier infinity, has now become 12. Why is that? Because I can now go from 0 and 10 and plus 2 and reach 5 and 12. Similarly, 2 to 5 has become 3 because I can go from 2 and then come to 5, right. So, there is an edge from 2, and so basically passing through 1, now I can take anything which points into 1 and then anything which points away from 1 and I can get an update. So, similarly 6 to 5 I can go minus 4 plus 2, so I can get a net weight of minus 2 from 6 to 5. So, SP2 has some interesting new distances. Now that I have discovered distance in SP2, right, I can now look at SP3. So, SP3 allows me to go through 0 and 2, 0, 1 and 2. So, if I go through 2 for instance, it turns out that I can now actually do things which I could not do before. For example, look at 5, right. Earlier I could not get from 5 to 5, but remember that we said that there are some cycles, right. So, now if I go from 5, I can go, if I am allowed to go to 2 and 1, I can go to 2, 1 and then come back to 5, right. So, now I have a cycle from 5 to 5 and there are no negative cycles we assumed. So, therefore, we find that 5 to 5 has length 1 because it's minus 2 plus 1 plus 2. Right? So now I have all these paths which get constructed. So for example, now that I am allowed to go through 2, I can find a way to go from 5 to 3, right? Minus 2 plus 1 is minus 1, right? So 5 to 3 also is a new entry because 5 points to 2. So in basically adding 2, you can check in this particular graph, the only incoming edge to 2 is from 5. So the only new things I will discover are in this row for 5 because these are the only new things that get enabled by going through 2. So I keep going through like this, and eventually, for instance, after I have done pass through 0 to 6, I have come with this matrix, and then if I go from 0 to 6 to 0 to 7, then I stabilize, and this turns out to be my final thing. And in the final step, I get these entries, right? And if you go back and look at the Bellman-Ford example that we did last time on the same graph, you will find that Bellman-Ford found exactly the same things as the shortest paths from 0 to all the other vertices, which is what you would expect, because among the all pair shortest paths in each row are the single source shortest paths for that row, right? And notice that some things are not reachable, right? So from 5, no matter what we do, we cannot reach 6. Okay? And it's not symmetric because from 6 we can reach 5, but we can't get back from 5 to 6. So this is an interesting thing that, you know, it kind of tells us things about the structure of this graph which may not be very obvious when looking at it. Now again, this is a very simple thing to implement like Bellman-Ford because it's just a bunch of nested iterations, right? So what we have to do is we have to keep track of the shortest path matrix. So what is the shortest path matrix? It is of the form SP K I comma j, right? So this is n cross n, and this one starts at 0 and goes up to n, right? So I need n plus 1 versions of this matrix to go through the different stages. So the shortest path matrix is n cross n for the I comma j vertex pairs, and k n plus 1 for the number of iterations that I go through. That's the index k that I am talking about, right? So I start off by setting up this matrix, right? So first as usual, I read the input weighted adjacency matrix. I find out this suitable candidate for infinity, right? And now I will set up the shortest path matrix to be a 0 matrix with n rows, n columns, and n plus 1 dimensions in terms of the stages that I am going to construct. So the first step is to construct the 0th stage, right? So I want to say the 0th stage. So 0th stage, I initialize everything to infinity, right? And then having initialized it to infinity, what I do is for every edge in my graph, so for every ij for which this adjacency matrix has one entry in the 0th column, I set that shortest path to be the weight, which is the one entry in that column. So remember that W mat ij 0 tells me whether there is an edge or not, W mat ij 1 tells me what is the weight of that edge. So this is the initialization, right? So this is basically setting what we had earlier called SP0 of I comma j. And now we just do this very trivial iteration, right? So from 1 to k, or 1 to n rather, right? We just go through every pair I comma j, and for every k we just say what the equation said, which is either we keep the shortest path. Remember, there it was in terms of k plus 1 and k, here in terms of k and k minus 1. So it's just a slight shift of notation. So there we talked about SP k plus 1 in terms of SP k. Here we are talking about SP k in terms of SP k minus 1. So SP k minus 1 of ij, or SP k minus 1 of I k minus 1 plus SP k minus 1 j at level k minus 1, right? So this is just the either you have a new path whose weight is shorter going through the new vertex k minus 1, or you have the old path which did not need it at all. And then finally, you want to return the last kind of, so you have these n plus 1 levels at which you computed the shortest path. So you want to return the last one, and that's the one which is at index n, which is this column, number of columns in my thing, right? So this is what we get. So this is the implementation, very straightforward, like Bellman-Ford. It's just a bunch of nested iterations, right? So when I initialize it, update it and so on, it is very clear that this particular thing is n cubed, right. And once it is n cubed, it is quite easy to see that nothing much is going to happen if you use, because we actually have to literally, I mean this is not a question of edges, it is not like Bellman-Ford where I am, or in Dijkstra where I am updating something based on the edges. I am literally saying for every pair I comma j, compute a better value for I comma j. So I have to do this n squared calculation every time, regardless of whether there are direct edges or not. So having an adjacency list does not help at all. So I might as well just write it in terms of adjacency matrices. If you rewrite it in terms of adjacency lists, you will find that there is no improvement in the complexity. Okay. But one interesting thing is there, which is that notice that when I look at the kth step, what I am looking at is the k minus 1 step. So I should think of this as having these kind of, so this is my SP0, then this is my SP1, this is my SP2 and so on. So I am basically computing this shortest path matrix in stages 0, 1, 2, 3, k. So, but in order to know the entries for k, so I initialize the entries for 0, then I get the entries for SP1 looking at SP0. So that's, if you look at the way we worked it out, this is exactly what we did, right. So we said if I know SP0, then I can get SP1, right. If I know SP1, then I can get SP2. So in order to get SP2, I don't need to know SP0 anymore, I can throw it away, right. SP0 is done. Similarly, from SP2 I can get 3, from 7 I can get 8 and so on. So what we are really saying is that we only need the previous slice in this, so this particular thing here, I only need the previous slice in order to compute the current slice. So in principle I have this n cubed sized matrix which I am using to calculate shortest paths, but we are saying we only need 2 n squared slices of it. So I can actually reduce the space from n cubed to n squared, right. So I maintain the current slice and the previous slice. So I maintain the, I have the previous slice, I compute the current slice, then I say okay, now this is the current slice, so I make this the previous slice. So I just keep updating, right. I throw away the previous slice and make this the previous slice and I compute the next slice from this. So I need to keep only the current copy of the SP to the power k and the previous copy SP to the power k minus 1. So though the time complexity cannot be really improved, the space complexity in this case can be improved. So to summarize, Warshall's algorithm is a different way to compute transitive closure, and we can now adapt it, and this is the Floyd-Warshall algorithm, to compute shortest paths, right. So the shortest paths tell us in this algorithm how to get from I to j by going through a prefix of the vertices from 0 to k minus 1. So this again works with negative edge weights assuming no negative cycles, and it has a very simple nested loop implementation. So it's very trivial to write the code for this, and it takes time order n cubed, and this order n cubed unfortunately cannot be helped because it is dependent, the n cubed comes from the fact that for every iteration I have to actually physically update every pair, every ij, whether or not there is an edge. So it's not proportional to the number of edges in the graph, it's just proportional to the square of the vertices. So it's always going to be order n cubed. However, by doing this trick of reusing the slices, right, SP k minus 1, SP k plus 1, I throw away k minus 1 and use k. By keeping only 2 slices of this thing, I can do this calculation using n squared space rather than n cubed space, which can be a saving.